This is a video for AQA Discrete Mathematics. This is Linear Programming section 1.4, where we're looking at the integer solution of linear programming problems. Well, we saw in earlier videos that if we plotted the constraints onto a graph, we could then use the graph to find the optimum solution. This we looked at using Vertex Method, where we checked every single vertex, and also shortcut that a little bit by looking at an objective line to decide which of the vertices gave us the optimum, whether it be a maximum or a minimum that we're looking for. Now, in those problems that we looked at, we were assuming that the variables that we had, the x and y, could literally be any values within the constraints. In practice, however, we have integer solutions. So if we look at the example that we did in earlier videos, you can see that the white region there is the feasible region, and there are many points there that are non-integers, of course. So if we were to constrain ourselves to integer solutions, then we'd have to decide which of the crosses there gave us our optimum. Well, here's the solution that we did with the maximization. Remember, there's the line for our objective function, which was p is equal to 3x plus 4y. So this particular one, I've taken a value of p equal to 12, and therefore this crosses the x-axis at 4 and the y-axis at 3. So that particular profit equation is 3x plus 4y equals 12. So that gives us one way of putting an objective function onto the graph. Now we can move parallel to that, so that if we want to maximize it, then the line moves towards the away from, beg your pardon, the origin, towards the top part of the feasible region, so that the last point that it exits from is here. So this is our optimal value, or our optimal point, which for maximizing in that particular question happens to be an integer. So we could say, even for integer solutions in this question, then yes, our maximum is when x is equal to 2 and y is equal to 3, giving us a value of p equal to 3 multiplied by 2 plus 4 multiplied by 3, which was 18, which is the value that we found in the questions in earlier videos. If, however, we look at minimizing, and we do the same thing, this time we're going to be moving towards the origin, so that the point that we reach as our optimal point is here, but that's a non-integer solution. So what we need to do then is to think about, well, which was the last integer. And if we just go back a little bit, you can see that as it moves towards the origin, then this one here must be the final integer solution. So our integer solution would be x is equal to 1 and y is equal to 2, giving us a value of p equal to 3 multiplied by 1 plus 4 multiplied by 2, so giving us a value or equal to 11 as being the minimum. Now, in that particular case, the integer solution was quite close to the non-integer one, but that's very much dependent on the gradient of the line for p. This one is quite different from the gradient of the side of the feasible region. However, you do have to be careful. It was okay in this one to see that this value here was not the final point, but had that value of gradient being slightly different, it could well have been this point. So you do need to be very careful, and I'll just illustrate that with another example in a second, where the integer solution is not that close to the non-integer one. So let's look at this question then, where the feasible region is in the centre there, and we've got the coordinates of each of the vertices. The objective function this time is p equals x plus 3y, so we need to start off by putting in some function which has got the correct gradient. So for example, we could choose x plus 3y equal to 3, in which case we would have the following gradient. It's going through x equal to 3 and y equal to 1. So here's the objective line, and now if we're going to maximize, remember we're going to move away from the origin as far as we can, and if we do that, then you'll see that the final point that we get to is at B. So our optimal vertex is B, which is 1.53. Now that would then give us a maximum value of P being equal to 1.5 plus 3 multiplied by 3, which is 11.5. However, of course, this is a non-integer solution, so had you been asked to find a non-integer solution, then that would be it. But if we're asked to find integers, then we need to look at where are the integer values within the feasible region. And there they are, the ones near the top anyway. Now, looking at that carefully, the one which the line crosses finally, before it leaves the feasible region, is this one here, close to A. So although the maximum point, the optimal point, is at B, the actual integer solution would be the one that I've indicated there, which is close to A, which is x equal to 3 and y equal to 2. So x equal to 3 and y equal to 2 are the integers, and then our value of p would therefore be equal to 3 plus 3 multiplied by 2, giving us a value of 9. So a long way away from the optimal point, and that's the one slight problem that you might have, is making sure that you've checked the final integer solution. If you're in any doubt at all, check all the ones that you can see which are close to the correct side of the feasible region, to make sure that you have the maximum or the minimum. Okay, that's the end of this video looking at integer solutions, and indeed it's the end of the series of videos on linear programming.